So, hello, my name is Din. I hold on this slide not because it's an awful picture of myself, but just to stress something in the title. I'm going to be focused more on the actual data itself and analysing that data. So I'm not going to do anything to do with the modelling, machine learning applied to that data. I'm really going to be advocating for a strong, well-principled, scientific data analysis analysing step before your modelling procedure. So I'm not going to try and sell you a new statistical method that keeps up at data rate. I'm not going to say that I'm going to sell you a new machine learning method that is 110% accurate, right? This is not what I'm here for. As you can tell, I'm not an engineer. I'm not wearing a shirt. I'm a statistician, right? So I really handle data. And what I'm going to really drive home, hopefully, in this presentation is looking at your data carefully should inform your modeling process afterwards. And if you do that carefully, you can do a lot of the work in that analysis stage. And my co-author, Niall Adams, is also a statistician at Imperial College London. So I'm going to be talking about a particular project I've been working on since, 2.5 years ago. And this is in collaboration with a unit here in Cambridge. So that's the Centre for Smart Infrastructure and Construction. So they approached me with data from this steel concrete railway bridge, and during its construction, within actually the bridge itself, it was installed with a fibre-optic network. So this is fibre bag gratings, if you know technology. And there's approximately 130 of these sensors. So just to hold the aim, but I'm not really concerned with the engineering application, more the data itself. The main aim really is to detect evidence of deterioration over time using the sensor data. And as you're well aware in the audience, there's many approaches to doing this. And one way of doing this, which I'm going to focus on in this talk, is solely by looking at a data-driven approach. So I'm only going to use the data, nothing to do with physics-based models, nothing to do with finite element models. Okay? So let's dive in and talk about the data in a bit more detail. So these are fibre optic cables. 1 meter apart, they are inscribings. These are the gratings. And these are located in various locations in the bridge, on the girders, in the sleepers, in the midspan, for example. So we've got a distributed sensor network, so we've got a distributed data set. What they record, the analyzer of that sensor network records, is wavelength of it over time. So light is shined or shone, don't know the correct term, through a cable of glass. The gratings refract the light at a certain frequency. When it bends, the distance between the grating changes, and that's the change in wavelength that we record. So that's the rawest form of the data we have. And this corresponds mostly for vertical deflections in the bridge at the various locations. I've come to know that wavelength is useless for you engineers, so you like to convert it to strain and then later into things like moments and curvature. But I'm going to be working mainly with the raw data, the wavelength, and the linear transformation to the strain. So we've got a spatially distributed sensor network recording things over time, spatial temporal data set. In terms of how quickly we acquire the data, there are 250 data points per sensor per second. So if we let this run continuously, this monitoring scheme, we're going to run into a big data problem in terms of the velocity we acquire the data at. So what I just plotted here, just to show you, just to look at the data, is the same passage, same 20 or so seconds of passage for two different sensors in different locations. So we've got nothing happening on the bridge, presumably, for the first 10 seconds. Then you've got kind of this train passage event, this train going over the bridge. This is the Bart Simpson's hair, right? And you've got the inverse for this sensor over here. So just by looking at this data, we see certain features just come out at us. Right? We've got the inverse of the dominant feature for sensor 1 and 21. This is just because of the difference in locations. These are on the eyes of the girder, one's at the top, one's at the bottom. One's in a state of compression and one's in a state of tension. That's why it's bending the other way. But if we look more closely, and this is a bit more subtle, but we can come on to this later on, there seems to be more noise in this kind of null state, the no load state, than this over here. So what I'm going to do now in the next slide is zoom in, and perhaps zoom in on a part that you may find not really interesting at first glance. What's happening when there's nothing, presumably, on the bridge, right? No train on the bridge, that is. I zoomed in 5 seconds worth of data now, and what I've done is plotted it not by connecting the lines, but actually showing the individual points. So by zooming in, we see a striking feature come out at us. There's banding here, right? by banding, I mean there's only several seemingly values the wavelengths take over time. And if one line of code or two lines of code, you actually realize that over 15,000 data points, there's only 23 unique values. And this number, this unique value, varies by sensor. So you remember that big data problem we had? Do we really have a big data problem? There's only 23 unique values. Let's go a step further and link it back to the modeling stage, right? What can we inform in terms of the modeling step in our process? These data are not Gaussian. Right? It doesn't look Gaussian. You can do a statistical formal test to test whether it's normally distributed or not. And it's not even continuous. So when you come to write down your model, your linear model, and you've got the epsilon term, the noise term, you're saying this follows a normal distribution, zero mean, and variance sigma squared. This is not the case, right? There's no discernible pattern or apparent signal in these data. So I was harking back in my brain to the physics, right? Physics-based models. Either it's a constant, no strain, nothing on the bridge, or there's modal frequencies. But Fourier analysis and other kind of cruder time series models reveals no pattern in this, right? So as a summary for this slide, like I said, I'm not trying to sell you anything, but trying to tell you how this can inform your process of thinking about modeling later on. The sensor system by itself is subject to its own noise process, which does not obviously depend on the status of the bridge. So I've looked at a short time period. This is 5 seconds, and before it was 20 seconds. The next thing I asked them to give me, the engineers at that unit, was a longer time series. So this is multiple events, and the Bart Simpson's hairdo is now these spike events. The time period is so long, these look like anomalies now. So this is approximately 600,000 data points, 40 minutes worth of data. So you see there's some sort of temporal variation as time progresses. So I'm going to click the next button, and I'm going to overlay another sensor on top of this. Just in a different location, and then here's another one. So that's unknown variation, which may or may not be due to temperature, right? Presumably it's temperature, but we need to do a bit more investigation. So as was hinted by that question earlier for the previous talk, machine learning methods have a difficult time tracking these unknown temporal variations. So if you were to train on that side of the data set, you have no hope of getting that sort of prediction from your machine learning method without actually inputting more than just the data. So these temporal variations poses challenges for the analysis of these types of data, or more succinctly, these data are not independent now, and they're not identically distributed, so epsilon is not IID. So I've been talking about individual sensors, right? Just singular sensors and overlapping plots. Look at something more collectively, and this comes back to PCA. So again, I'm focusing still on the no-low data. I'm not even interested in what happens when the train passes over the bridge yet. So I'm going to take the no-low data over the 134 sensors. So I'm deleting that part in the middle. I'm going to pass its covariance matrix through PCA. And this is what the first two scores give me. Now, anyone that's done PCA would be looking for clusters and groups and then doing cluster analysis on those and saying this is different. This is very unusual in the literature. And this is what we presented in the paper as well. So the first two components explain 42% of the variation in the data, and the remaining individual components explain very little. Now remember, this may look low to you, but remember, nothing's meant to be happening on the bridge. This is meant to be noise. So remember, sorry, I probably skipped a bit fast over principal component analysis. Principal component analysis is just basically a rotation of your data, right? It's an orthogonal transformation. So what it's really doing is capturing the information from all 134 sensors into this two-dimensional object that explains the majority of information in terms of variance. Or more compactly, I'll combine the information over space and time into that two-dimensional object. So the individual slides before were answering questions. You can use those features to answer questions of individual locations. This is about the collective response of the entire network now. I'm saying you don't need to understand 134 of them. You need to track that, potentially. So in summary, the physics that governs the response of the bridge to various stimuli is not what's being captured by this 2D structure, this donut. This is an artifact of the sensor network. And this is present in the sensor data when there's nothing on the bridge, right? And more importantly, sorry, this couldn't fit on the previous slide, we've got another bridge which presents some sort of similar 2D structure as well. So it's about the sensor network now we're talking about predominantly, not necessarily the bridge. How much time do I have left? Oh, thanks. So let's link this back to kind of aims, right? Goals. I know you're engineers and you're thinking, how am I going to link this back to assessing the performance of my bridge, structural health monitoring challenges? And how the hell am I going to use that donut to answer my questions, right? Well, let's link this back. Let's take the word health and expand. Let's talk about human health, right? So I'm based in Imperial, South Kensington. I play football regularly in Hyde Park. I exercise, right? My heart rate increases when I exercise. If I stop exercising, my heart rate. That period between stopping exercising and going back to my resting heart rate could be an indication of my health. If that increases over time, something could be wrong with me, right? For example. What I'm saying is that that is the resting heart rate, or could be considered a resting heart rate. Right? How long it takes to get back to that after a train passage event may be of interest of monitoring over long periods of time. That's one way of doing it. I'm not saying that's a good way. That's just one. And operating on that 2D latent structure is much easier than 134-dimensional object. So my last slide, so don't worry. Again, there's no punchline here. I just want to promote good practice, that's all. So inspect your data carefully. Visually, look at the data. If I didn't plot the data individually or with the lines, I wouldn't have found that banding pattern. The sensor noise may not be noise, and by that I mean not white noise, for example. And understanding that sensor distribution or noise will lead to more accurate statistical models. Latent structures are typically easier to handle. It doesn't need to be PCA, it can be anything you want, anything to project down into a low-dimensional space. And if you want to do detection of anything away from that, anomaly detection is usually easier on those lower dimensional structures. I think you may even avoid some multiple testing problems if you know what they are. And I just want to end on this kind of just taken from the paper, but I thought it's worth reiterating and putting as a last line in this talk. So always remember that the data that you capture captures the response of the physical access through that sensor network. And both the physical structure and the sensor system is subject to environmental factors. So any conclusion, any scientific conclusion you make based upon these data refers both to the physical asset, the environment, and the sensor network. So that's all I had. Thank you for your patience. Thank you for having me as a statistician, by the way, as well, and not an engineer. When you take care.